And then if it is, then you know it's not positive. You just say, okay, it's not positive. And then now you assume that n is not here. And then you check whether n is 3 SOS, right? If it is, then you know n is positive, so you're done. You say yes. And then you check whether, after that, you check whether n is n plus, if not, then you check n plus 2 is 3, sum of 3 squares or not. And if it is, then you say yes, my integer n is positive, right? Because we cannot make a mistake that if n is not in this set, then either it's like less than minus 2 or it's bigger than 0. And because if it's less than minus 2, then both n and n plus 2 cannot be sum of 3 squares, right? So we always can verify uh, positivity of integer using an oracle for sum of 3 squares. Right. Now, I want to somehow relate this problem 3 SOSLP in the other way. So we saw that under oracle reductions, for SLP is sorry, 3 SOSLP is as hard as for SLP. I want to say something in the other direction now. For this, I need to introduce this problem, which is quite similar to DEG SLP. So here you're given SLP, which computes the positive integer n, and you want to decide somehow whether the 2 to the L divides the absolute value of n, right? Where L is also given as input, some positive integer. Yeah, so one can show it's not too hard. We show on the paper that this div2 SLP is as hard as this open problem like SLP. Yeah, also it's also quite natural, right, that this div2 SLP will be useful for deciding 3 SLP, because the condition was that it should look like, so a number is not 3 SOS if it is of the form 4 to the a times 8b plus 7. So it has to do with some powers of 2. And so it's quite natural that this oracle will be useful for deciding 3 SOS SLP, right? And we show in the paper that if you have both the oracle, if you have access to both the oracle, SLP oracle and this div2 SLP oracle, then you can divide these 3 SLP in polynomial time, right? So it would be nice if we somehow could avoid this div2 SLP oracle. Then we would basically get that the 3 SLP and SLP are equivalent under Turing reduction, but this somehow, yeah, this we cannot do, at least right now. Yeah, essentially, yeah, the proof is essentially that you first check whether n is zero, positive or not, and then you use deep to SLP oracle to check this condition of this 4 to the a times 8b plus 7 or something. Right now, we come to sum of two squares. So a criteria was proved for integer being sum of two squares by Gauss and Jacobi. They showed that if I look at the prime power decomposition of n, so this prime power decomposition will have primes of form 4k plus 1 or 4k plus 3. So as long as there is no, so if there is a prime of form 4k plus 3 which has odd power in the prime power decomposition, then it cannot be written as sum of two squares. Otherwise, it can always be, right? And this theorem you can use that this PIT or equal SLP also reduces to 2 SOS SLP. Essentially, you can show that this integer 3m square cannot be a sum of two squares. Right. And also in the paper, we don't prove that this PolySLP reduces to 2 SOSLP. First of all, we prove that it's like if you use it's only in NP related to the to SOSLP oracle, not in P. Also, and we don't prove it unconditionally. We need this conjecture, this Kramer conjecture, which deals with density of primes in arithmetic progressions. So this conjecture is quite a strong conjecture from number theory about distribution of primes, and yeah, we need this conjecture for this theorem to be true. Right, and so you can also consider the case of like one square, right? Whether a given integer can be written as square. Uh, this you can also prove is like all these problems are at least as hard as PIT or equal SLP. And yeah, you just consider this integer n square plus 1, and this is square if and only if n is 0, right? If n was not non-zero, then this thing cannot be a square. And we, in a previous paper, we also proved that this at least this thing has an efficient random algorithm, right? Assuming GRH, so generalized Riemann hypothesis. And the idea is that basically you decide if n is a square of integer, you just you compute it modulo a random prime p, then whether check whether this n mod p is a square in the finite field Fp, right? And using the Chebyshev density theorem and GRH, you can prove that this succeeds with constant probability. So we also look at instead of positivity for integers, we also look in this paper we also look at the positivity certificate for polynomials, right? So analogous to integers, you can also ask that suppose I am given a univariate integer polynomial computed by a arithmetic circuit or straight line program. I want to decide whether this is positive, right? What do I mean by a polynomial is positive? So when I say a polynomial is positive, I mean that it's like it evaluates to it's non-negative on the real line. Okay? Right. And so this there is a theorem, this folklore theorem that which says that every uh, every positive polynomial can be written as sum of two squares. Right. But these polynomials, this G and H might they might be real polynomials. But there is a rational variant of this theorem also known. Cauchy proved in 71 that if I have a rational polynomial, then I need at most five rational polynomials. Uh, if I have a positive rational polynomial, then I need at most five rational polynomials, so that I can write f as sum of squares of these GIs, of these five polynomials. Right. So now you can, analogous to this Lagrange four-square theorem, you can also look at these possibility certificates for polynomials. And so there is a possibility variant of polynomials also. And here we ask whether a given polynomial f is positive, right? So we don't know any hardness results for checking whether integer is positive or not. But this problem can be proven to be co-NP hard. Okay, so at least for checking positivity for polynomials is we prove it to be co-NP hard, but it remains open for integers. And we also look at this problem where you are given a polynomial f. You want to decide whether it can be written whether it's a square of another polynomial, right? So note that we cannot simply compute, if suppose f was g square, we cannot simply compute g, right? So circuit size for g might be very large, right? So we cannot just compute g and then check whether f is g square or not, right? But we can use this oracle for square SLP to solve this. And essentially, there is a result by Murthy who proved that a polynomial is square if and only if I evaluate this polynomial f at all any integer t, then it will always be perfect square, right? If f is a square, then this condition is always true. And he proved that if f is not a square, then there will be some t where f of t will not be perfect square, right? And then yeah, by using some effective variant of this lemma, you can prove that this problem is also in co-RP. Also note that there is no restriction on the degree of f here. So degree of f can be exponential. Right? If the degree of f was polynomial, then I can actually compute f g by using uh, some Taylor approximation or something, right? So and then we also show in the paper that this problem of deciding whether f is a square of a polynomial is in co-RP, and the idea is essentially that you pick some random number t, some random digit t, and then check whether ft is a square. And this we can check by using this algorithm for checking whether a given integer is square or not. We already showed that this is in co-RP, and one shows that this succeeds with constant probability, and for this one needs some effective variant of Hilbert's irreducibility theorem. Right. Okay, to summarize, somehow this is the complexity landscape now after this paper. So this order SLP is the problem where you want to check whether a given power of x divides a given polynomial f. And so in the paper somehow we made this the diagram of landscape richer now. We introduced this problem 2SOS, SLP, 3S SLP, and also this problem deep 2 SLP, which somehow it's surprising that also it not very surprising, but it's interesting that it relates to this known problem tag SLP and also somehow to this new problem 3S SLP. Right. So for the future work, like this new problem, I think it's quite interesting. Like it relates to like SLP in a very natural way, and we do not know any hardness results for DEG SLP. Can we prove at least some hardness for DB2 SLP, right? And how does like it somehow seems to have no connection with PowerSLP as of now, but it might be interesting to somehow see if there is any connection of these two problems. And yeah, so we in this paper we did not look at complexity of like let's say I want to check whether a given polynomial is sum of two squares or three squares and so on. This polynomial analogs of two SOS and three SOS SLP. This also might be interesting. And also, yeah, like a big major, I think somehow a shadow of this talk is always that all this PowerSLP business, this somehow is always the open question, right? So can we prove NP hardness for PowerSLP unconditionally? Also, yeah, so I think even like very special cases of PowerSLP are not known to have efficient algorithms. So even this example which I showed you on the first slide, right, this a to the n plus b to the n minus a to the n, even for this case, I do not know how to decide the sign efficiently. But when a, b, c, and n are given in binary. Right? So these very special cases of PowerSLP are also well open for designing efficient algorithms. Okay, thank you.
I have a couple of quick questions. Any question? Okay, if not, let us thank the speaker.
Should we stop the share now or?
You talk to Kevin?
Yes, I had uploaded on the.
Do you know where it is?
I had uploaded on the like whatever that web page, the
I
link.
said, you know what is this?
I see.
The uploaded, he has uploaded the file there. So how do you?
No, you just press escape.
Escape. Okay.
You'll see from there. I don't know where it. I mean, so there is a link that was sent yesterday. I uploaded on that link.
दे दो दे दो
No, it was to be at. Whose office? लिंक पे दिया था ना कि वहाँ से डाउनलोड करना है देखिए I thought you uploaded this file. I wanted to download it.
इसको इसे शेयर करना है
I think Supposed to go back? Okay. Yeah, this hopefully is familiar. Yeah.
I'll just use the mouse and expand here. Okay.
You could also do that.
Oh, this work?
This also works.
No, but the pointer won't work.
Well, if you press and hold and move it around.
Press this. Oh, I see. White. Oh. Oh, well, I see. Oh, but it's a bit. Okay, sure. Let me try.
It's okay, actually. Sorry, I think you were the first to upload your slides.
Okay. No, it's okay. Should we start? Yeah, we can. Wait, what?
Okay, so sorry for the delay. So, oh, I see. Okay, okay. Okay, so the next talk is by Anamai, and he's going to talk about ROABP and partial derivatives. Anamai.
Yes, I can't seem to.
Okay.
Close display button instead of the previous.
No, this is just.
पीछे नहीं लगा।
Oh, I see.
पीछे और forward
ये फॉरवर्ड ये पीछे है नहीं ये देखो
Oh, if there is one blank.
No. Okay, हाँ मैं इधर से करता हूँ ठीक Is it also blinking, right? I mean,
Yeah, it is.
it's okay, I guess. I mean, we'll make. Okay, so yeah, okay. Thanks, Bireshwar, for the introduction. Yeah, so in a complete contrast to the previous talk, the proofs, the math behind all these results is quite deep. So I will not go into the math. I will try to make intuitive sense of like I'll try to convey the intuitive ideas to you. So we do build what are called explicit commutative ROPs. I'll tell you what they are from partial derivatives, as the title says. But for the talk, I'll just stick with the example of determinant. I'll tell you how to construct commutative ROPs for the determinant, and I'll tell you what those things are. Okay. So let's start. Yeah. So here is the determinant. You all know this polynomial. For any n, you can take n squared fresh variables, put them in a matrix, take the determinant. This is the determinant polynomial. We'll call it det n. If I ask you if you can write it as a product of univariates, what would you say? Anyone? Can you write it as a product of univariates? Okay, forget univariates. Can I write it as a product of any two non-trivial polynomials? You can't, right? It's an irreducible polynomial, so you can't write it. So, so yeah, but okay, so something has to change because so something other than the mic had to change. So what else has to change is, so if, okay, so suppose I allow you univariates that have matrices as coefficients. Okay. What do I mean by this? So see, now I will show you another irreducible polynomial that can be written like this. So let's say you want to write x plus y. Okay. So yeah, that squiggly, this approximation sign, I mean, I'll tell you what it means. So basically you can write it as a product of these two univariates, that univariate linear polynomials that have matrices as coefficients. And how you can see exactly like this. Basically the first thing simplifies to this matrix, the second thing simplifies to this matrix. Now if you take the product, you get x plus y showing up as one of the entries. Okay. So what we will mean by this squiggly sign is that you can write your polynomial as some linear combination of the entries of the matrix product. Right? You have univariates with matrices as coefficients in them. You can think of them as a single matrix with univariates as entries. You multiply those matrices, you will get some multivariates as your entries. Right? This product is supposed to compute your polynomial if your polynomial is a linear combination of all the entries at the end of the whole thing. Right? Yeah.
So only the polynomial should appear in the final matrix or other entries?
Polynomial need not appear. So if for instance you had x and y appear in this whole thing, I would still say you are computing. So I'll define it.
Yeah, so now this is the question. Can you write determinant as a product of univariates over matrices in this sense? Can you conjure up a product of univariates with matrices as coefficients such that in the final product you can now take a linear combination and write the determinant? Okay, so that's what we are going to look at. Okay, so this is the formal definition. I guess we can reduce it now. Okay. Yeah, so a product of univariates or matrices is said to compute a polynomial if this polynomial is a linear combination of the entries of the final product, right? Okay, yes. Yeah, so this means that there are some betas, like one for each entry of your matrix, such that now you can take the beta linear combination and get the polynomial. Okay, and here W is the size of each of the matrices that are appearing. We just assume that all of them are W cross W square matrices. So all the multiplications are legit and everything, right? So at the end, you give me W squared many, let's say, complex numbers, right? Or real numbers if you want to, it helps to think you, right? And here this W we will say is the width of this product. So now your product is no longer a single line. So now, I mean, it's possible that if I give you a large enough matrix, in fact, you'll see that is what will happen. If I give you a large enough matrix, you can compute anything. So you need some sort of handle on like what is the complexity of this product of univariates that you have written. So we will make that complexity measure the width of the matrices that appear. Okay. So now the question is, okay, now so here is the this is what I meant. So here is a fact. You have any n variable degree polynomial. It can be written as in this sense, it can be written as a product of univariate matrices, right? I mean, yeah, of width d to the n. Okay, yeah, before this is what an ROLP is. An ROLP is a product of univariate polynomials where the coefficients are matrices, and at the end you take some linear combination. Okay, so I say f has an ROLP of width w. If f can be written as a product of univariate polynomials where w cross w matrices are appearing as coefficients, and you take the final product and you take some linear combination of all the entries and you can get your polynomial. So you can think of the product if you have understood it better, but these two terms I'll probably be using interchangeably. Right, so for any univariate polynomial, I can write it as a product or an ROP of width d to the n. And why is this true? This is essentially true because since we are working with matrices, if you can compute two polynomials f and g as a univariate product, you can sort of take all the matrices that you have been using and align them block diagonally. So you can put the univariates that you are using for f here and univariates that you are using for g here. Okay, and then the same thing will go through. So your width just adds up, right? Which means you can, of course, you can compute any monomial. You just it can compute just a product of univariates, not even in matrices. So now you can line up all the monomials along the diagonal and compute it. Okay, so this means for determinant you can do it with determinant as n factorial monomials. So you can write determinant as a product of width n factorial. Can you do better? That's the question. Okay, any questions at this point?
It's just about the sparsity, that this is the maximum sparsity that it could be of polynomial. So that's the width of the matrix.
Currently it is just sparsity, but we can do something non-trivial. We as in, generally we will also do something non-trivial, but there are more things to come before that. Okay, yeah. So here is the theorem by Nissan from 1991. He had not stated it for other OPs, but it works. So okay, so yeah, so a lot of things, but okay. So what did he say? He said that you have any polynomial f, you want to write it as this ROVP. There is some measure that you can use. Let's call it n of f, n for Nissan, right? Which tells you exactly what is the width you need for the ROVP for f. Exactly, nothing, no order, nothing, this, exactly that width. So what is this n of f now? You are taking the maximum rank of n matrices, right? I'll now describe what one of the matrices is. So you have an n-variate polynomial. There are n matrices and in fact there are n-1 matrices. Yeah. So what is the ith matrix? It looks like this, the thing on the right. So it's called a coefficient matrix for the polynomial f. So what you do, you take a matrix and the rows are indexed by monomials in the first I variables, and the columns will be indexed by monomials in the rest of the variables. Right, so you are just copying the, you want to write the product of univariates, right? You want to see how much information you need to remember at a cut, right? So take any cut, right? So this is the I versus n minus I cut. So yeah, and this is, I mean, so okay, so there an entry which is where the 1 through I monomial is m and the I plus 1 through n monomial is m prime. The n prime entry is the coefficient of the product of those two monomials in your polynomial. Right? So this is how the coefficient matrix is defined. And turns out that the rank of this matrix or the ranks of these n minus 1 cut matrices exactly capture the widths that you require. There is a more nuanced statement, there's a final statement here, but for us, when we consider all widths to be the same, this is the statement. Look at the biggest rank that any of these cut matrices have. That is the width you need to compute F as an ROABP. Okay.
So one thing I want to ask is what is the order? So you're choosing.
So for now the order is x1 through xn. Soon the order will not matter. So okay, so and you'll see why. So the thing is, okay, so this settles it for determinant. Like if you want to ask what is the best width for determinant, this settles it. Determinant, we know the coefficient matrices have rank roughly n choose n by 2, which looks like 2 to the order n, I mean 2 to the theta n. So the question that I asked you, like on the second slide, what is the width required for determinant as an ROABP? It is 2 to the theta n. Okay. Yeah, but now you can ask for more. Okay, so what is the property that we lost when we went from product of univariates to products of univariates with matrices? Is exactly Weber's question. Like we now have to be careful about in which order we are multiplying them, because matrices need not commute. Right, so can you get better behaved products like things that behave more like a product? Right, so can you get a commuting product? Right, so good products commute, so you want your product to commute as well. So now this is the goal. You want to find univariates Mij's, right? Mij, Xij, like with W cross W matrices as coefficients, such that no matter in which order you multiply them, you can still recover determinant from the entries. Right? Is the question clear? But now you want a commutative product. And see, it can be done. Right? I'm not asking for too much. Right? So similar to this, I mean, remember the whole monomials and writing sum of monomials along the diagonal. This is exactly that construction. And since you are only getting diagonal matrices, you can swap them around. Right? So the trivial bound, in fact, holds for commutative products. Okay. Good. So, okay, so by the same logic, the same bound that we used earlier, determinant has a commutative, in fact, a diagonal, like it has an ROABP which uses only diagonal matrices, and they have width n factorial, right? But as you know, this is trivial bound, this is just sparsity, right? So can you do something better, like as he had asked, can you do something more non-trivial? So yeah, so there is one way of making, like getting a non-trivial commutative ROAP that we will first see. So this is a trick, I mean, it's called duality trick. It's a theorem by Saxena from 2008, right? So what is it saying? It's saying that if your polynomial that we want to write as an ROAP has some special structure, then it has non-trivially small diagonal ROAPs. Right. So what is the structure? If your polynomial f can be written as a sum of df power, so let's say f is homogeneous of degree and so on. Okay. F is a degree polynomial, assume it's homogeneous. If it can be written as a sum of df powers of s many linear polynomials, right? Then it has a commutative, in fact, a diagonal product of matrices of width that is poly in all these parameters, in fact, linear in each of the parameters, like NDS. Okay. So this is the thing. So this might give us something for determinant, right? It turns out it does not, I mean, not much. So the best such representation, like this is called a Waring representation, but not important. So best representation of determinant as a sum of powers of linear forms itself requires roughly n factorial linear forms. It's like poly in n factorial. It's not like the dominant term still remains n factorial, right? So we are not doing any super polynomial improvement over the trivial bound. Yeah, but remember, we are still using this diagonal matrices. What if, I mean, we are not really using the power of the freedom that we have to use any commuting matrices. So how do we bring that in? Right, you seem to need a more general trick than this. And that is what we do. So we show that determinant can be written as a commutative product in the sense that I've been talking about till now, of width that is basically polynomial of the non-commutative width that it has, right? The general ROP width was 2 to the order n, and you can get polynomially close to that. You can get, so that will look like n to n by 2, which is 2 to the eta n, like 2 to the n basically, 2 to the n over root n or something. And this will be 2 to the 2n. So it's like quadratically far from that, and you can make it commutative. That's the thing. So yeah, so the actual theorem is more general. We show it for any polynomial. So for any homogeneous polynomial f of, right, doesn't matter the degree also, it can be written as a commutative product of width that is equal to the dimension of partial derivatives. You don't need to know what that is. It's a measure that is slightly more general than Waring rank. I mean, than this, the Saxena's measure that I told you. It's not his measure, but for the purpose of this stuff, right? So some measure. So you can see it as a sort of a more general version of the duality trick. Like if your polynomial has this structure, then it can be written as a commutative product of smaller width. Okay. So this works for anything, but I'll tell you later why I chose determinant. But yeah, so this is the thing. So after this, I'll try to give you some idea of what the proofs are. So if there are some questions, I can take them now. Yeah.
Doesn't give a better one become.
No, that's not. Yeah. Yeah, okay. So yeah, so now let's look at some. Okay, yeah, so this is just for fun. Look at these 4 matrices. I mean, they are of size 2 and choose n. So the best thing I can fit on the screen and make it legible is for n equal to 2. But look at these 4 6x6 matrices, multiply them in any order, and determinant will appear as one of the entries. I mean, it will appear as a linear common. You can recover determinant any order, right? Okay. Generally, you have 2 and choose n width matrices. Okay. So how do you generalize this duality trick? Okay. So let's look at the proof of this. Okay. So let's simplify, right? Remember that sums won't hurt you, right? If you can always take sums and the width will only increase additively. So the duality trick says that if your polynomial can be written as a sum of powers of linear forms, it can be written as a diagonal ROVP. Just take one power of linear form because sums can be handled. Okay. So let's say you have this particular linear form, AIX, summation AIXI, and you're taking it to the dth power. We'll see how you get a diagonal ROP of width ND for this. So of course, I don't know how to motivate this, but for some reason you look at the Taylor expansion of e to the power L. Okay, it looks like, it looks like this, like 1 plus L. So the point is, in the Taylor expansion, so you think of L as the linear form that you have, right? Summation AIXI. Then what is happening is your polynomial, which is the dth power, is appearing as a term in the Taylor expansion of e to the L. Okay. This seems to not be very useful at this point, but this is a cool thing that exponential functions have. Sums become products, and that's what you want to do. So if you take e to the power a linear form, it is exactly the product of e to the power each of the xi guys. And this is product of linear in some sense. They are power series for now, but you have made progress, right? Now you observe that all you want is the d degree homogeneous component of this Taylor expansion. You don't want all the high degree things. So you can truncate each of your univariates to degree d. Right? And this is what it looks like. So you can just truncate each of them, take the product, and somehow you will be able to construct determinant. So I won't get into how you can homogenize, but you can do homogenization by you can write this expression as a sum of some variants of this expression, nd plus 1, many of them, and you take some linear combination appropriately, and you will get the homogeneous component. So this is how you get. what I want to bring your attention to is this step, right? In fact, especially this polynomial. Like look at these truncated exponentials, okay? And for a moment, forget this homogenizing operator outside. Just look at the product of the truncated exponentials. Okay. So this, let's say this is the important step. Like, okay. So, and because we want to do this generally for any linear form, let's put t as variables for those guys. Okay. So let's define g as this polynomial, which is the dx homogeneous component in the x variables of product of these truncated exponentials in tx. T are, think of them as your linear forms or something for now. Okay. Then what you can like sort of say was like the duality trick is that, I mean, so okay, so notice that this homogenization is exactly going to give you the linear form to the power d. Homogenization is what sort of took you this ND sum. So apart from that, it's just S evaluations of this guy at different values for t, right? The S different linear forms that you have. Have I gone too far? Okay, no. So how much time do I have?
12 minutes. 12 minutes.
12 minutes. Okay, yeah, sure. Okay. Yeah, okay. Yeah, so okay. So another way of stating this is that F can be constructed or F can be seen as a linear combination of evaluations of G at different like this values A1 to A as substituted in T. Right? Are you guys with me at this point? Maybe most of you are not, but anyway. So right? So, and I've been pointed, like I've been told this multiple times that this is a less simple way of stating this. So stated less simply, this is the same as saying that if I take this polynomial G and reduce it modulo a particular ideal, and this ideal is, what is this ideal? So, okay, so yeah, it sounds more intimidating than it is. So if you want to evaluate a univariate polynomial P at a point alpha, you can see it as you like finding the remainder of P of y when you divide it by y minus alpha. This is the multivariate version of it. You want to evaluate a multivariate polynomial at a particular point. It's similar to going modulo xi minus ai for ti minus ai for all of them. And if you want to go modulo s different things, then you like go modulo all of these s things and look at all those guys and take some linear combination of them and so on. Okay, so that is exactly what I mean. So, okay, but this is important because I want it stated in the ideal way. Okay, so yeah, so you want G. So okay, so what do we have? So we have that G. If you look at this polynomial G that has been defined at the top, and you go modulo an ideal defined by the S points that were given by the decomposition as a sum of powers of linear forms. Okay, then you get a diagonal RAVP for F. This is the statement that I want you to remember. So what do we do when I mean that, when I say that we generalize this particular observation? We use a slightly different ideal. In fact, it will turn out we use a larger ideal to go modulo similarly. And since we use a more general measure, like rather than using sum of product of the size of sum of product of sum of powers of linear forms, because we use the dimension of partial derivatives, instead of getting diagonal matrices, we just get commuted, like general commuting matrices, right? So this comes from this particular thing. You don't need to understand it. All that I want to tell you is that given an F, you can define some ideal called the A power ideal of F. And turns out that the ideal that you went modulo to do this duality trick, which you saw on the previous slide, that ideal is contained in this F curve, the A power ideal. Now, okay, ideal containment is a bit distinct. So think of integers, think of all integers that are divisible by 6. Okay. They are a subset of all integers that are divisible by 3. Right? You can, if you want to find what an integer modulo 3 is, you can probably do it by first going modulo 6 and then doing mod 3 on whatever is left. So if I give you, if you go modulo a smaller ideal, which is like multiples of 6, you still remember the information that is required to go modulo a larger ideal. And turns out this was what was happening in the duality trick. Because whenever you have such an expression as sum of powers of linear forms, you have a smaller ideal that fits inside the correct ideal to go modulo. You can still reconstruct your polynomial from like after you have taken mod with respect to the smaller ideal. But nothing is stopping you from going modulo this larger ideal directly. And that is exactly what we do. Turns out if you go modulo this larger ideal, the size of the matrices that you will get. So firstly, you will not get diagonal matrices always. I can give you examples offline of matrices that will not give you diagonal matrices. I mean, of ideals that will not give you diagonal matrices. But you still get converting matrices. And the good thing is their width now is equal to the dimension of partial derivatives instead of, okay? And this is, okay, so this is good for the determinant because determinant has much smaller dimension of partial derivatives than an upper bound for Waring rank that we know for it. Yeah. Is there a question? Yeah, no. Okay, so yeah, just summarizing now. So the duality trick gives you a way of going from a polynomial being written as sum of powers of linear forms to diagonal univariate matrix products, right? Okay. So, but for example, for determinant, what will happen is that this will give an expression of width that is roughly n factorial, like some poly in n factorial. But we know that if you let go of commutativity of these matrices, then you have a much better expression of 2 to the order n. So the question is, can you get 2 to the order n commutative product? And turns out you can do this by going modulo the apolar ideal. And this is what we did. Yeah, and as I said earlier, since we work with a weaker guarantee, so what do I mean by weaker guarantee? It is known that if you have, yeah, I mean this, right? Look at this. So yeah, so it is known that if your polynomial can be written as a sum of s many powers of linear forms, then it has small dimension of partial derivatives. The inverse is not known. I mean, sorry, the converse is not known. Okay. So in some sense, when you only assume a bound on dimension of partial derivatives, it is a weaker guarantee. Since we use a weaker guarantee, we get weaker constructions. We don't get diagonal matrices, we get commuting matrices. But for determinant, it shows you a super polynomial gap, right? This has some other connection to this partial derivatives versus Waring rank question, and all those things are there in our paper. You can read it, but I thought this was sort of more important. Yeah, so I'm done. Thank you.
Are there any questions? This, but is it possible to design diagonal piece without using the duality trick?
Not entirely sure at this point. So yeah, I think I'll take so whenever you give me a diagonal, you get some sort of a different ideal that is like radical, like similar to the ideal given by the given by the sum of like this Waring decomposition. But yeah, I'm not sure if it's a I mean I'm not sure if you give me a diagonal, I'll be able to. So I can give you one example. So the symmetric polynomial does not have a small Waring rank, but still it can be written as a diagonal of small width.
Okay.
But yeah, so it's not true in the exact sense.
Okay. Yeah.
But yeah, so there could be something deeper I can talk to you offline.
Any more questions?
So let us thank Anamai. So we're running a little late, so we're going to start at 11:50.